Yeah, I think we're all set for another day. Hello.
Hi everyone.
Hey, how are you doing?
Yeah, doing well. Doing well. I was reading this paper today on brain drop.
Uh-huh.
Yeah. I saw your name there. You're among the authors. So because I was really, I think was it last week we're discussing on actually the way forward in analog and digital. So I was looking at how we can actually move forward, beyond today. I've seen brain drop, and now we can actually still push the frontiers. But if I may ask, what else needs to be done both in digital and in analog, basically? But I know that you're focused on analog right now.
Yeah. In terms of what still needs to be done, I think mostly it's that we need more people just working with these things. In particular, I think the one big thing that's missing right now is just tools, well-polished tools to try out different things, to try different applications of these. I think that's one big side. Another big side is the interfacing. Right now, most of the times where I've like come out, oh, this is an interesting use that I want of this analog hardware. But it involves sort of, oh, okay, well, here I've got my analog processing. Here's the sensor I want to connect it to. And then I've got to put a giant FPGA in the middle that sucks up all the power. And so figuring out ways to deal with that is, I think, a really interesting challenge, to doing that in sort of interesting generic ways. And just getting them in the hands of more people. Figuring out good ways, even actually it's going to be one of the points of discussion today is, hey, people are coming up with this interesting analog hardware, but it's just no one can get access to it. So how can we provide remote access? Can we provide tools for that sort of thing? So yeah, I think my feeling is like things like brain drop and things like FPAs have really demonstrated that this stuff is incredibly useful and can give the power advantages that everyone's expecting. But now it's a matter of time. Okay, now we got to actually push things forward and make sure people can access it and make sure lots of people can try it. And the initial flag has been planted to the ground that yes, this works. Now we got to do all the details. Does that sort of answer your question?
To some extent. That there's this argument about SNN and its significance really and pushing forward. And I know last week we had that discussion of someone saying that SNN is not really that important, ANN and all that, So there was still some both sides arguing. But if I may ask, is SNN actually the best abstraction closest to the brain right now?
So there's going to be definitely lots of different ways of playing with the word best there, and it'll always be the, well, best for what? I would definitely argue that right now on digital hardware, I am completely convinced that spiking gives you a really big power advantage. I'm less convinced on spiking giving you computational advantages. But all of the reasonings that I've seen so far for spiking giving advantages are really relying on a lot of digital assumptions. And I don't know, I think, yeah, I'm really curious how that question changes as we start getting down into analog. I don't know if Jennifer has a different answer.
I think there's lots of good things to what you said there. I think my perspective is I think that spikes can be incredibly useful for power efficiency and for energy efficiency and for efficient implementations, but it has to be handled correctly. And has to be handled a lot more how biology uses it. And I think that's where the rub is. Because most typical techniques actually don't make it worse. And so the problem then is understand, and I think part of it is an understanding of neuroscience and understanding how we approach those things. So that's I think where the question that's where my opinion is. But yeah, I am a firm believer that we will find that spiking networks will be quite power efficient in the long run. Very firm believer.
I have an opinion if anybody wants to hear.
Sure.
Hi,
Sure.
Steve.
Opinions are
Okay.
good.
All right. Well, later today, Terry's going to be talking about how neuromodulators allow for multiple functions of a neuron in different networks, the way Eve Martyr described the other day.
Right.
And I think the same goes for spike timing in dendritic trees. Depending on the arrival
yes.
times of spikes in the trees and which neurons are spiking in the tree at any given moment, a neuron can participate in multiple different networks contingent on the context it's operating in.
Mm-hmm.
I think that's a big deal that nobody knows how to test yet.
I think there's a couple conversations of it algorithmically, but very, very few. I so strongly agree with your dendritic conversation. I will just amplify that up for you. I do find it interesting. Everybody who's usually spent enough time to dig deep into the dendritic stuff has usually been pretty amazed by what could actually be possible.
Mm-hmm.
But for some reason, that's not very popular.
Well, it's it's one of those things that's hard to measure, and let's stick with the low-hanging fruit. Though it's what everybody has to do.
Well, but here's the funny part: is it doesn't get built very often. And it could be built, or we could be getting ahead of the game. And there's been a couple things, but we typically just don't, which is an interesting question.
Mm-hmm.
So, for what it's worth.
Sure.
Yeah, no, I just amplifying what you're saying, and I appreciate it.
I definitely agree. We have a student at Waterloo, Andreas Stockel, who's done some really great simulation work with doing nonlinearities in the dendrites and showing how that increases the class of things you can compute with a small number of neurons. And that's actually high on the list of things that would be really nice to go and implement in FPAAs and go try. So I see a hand up over there. So
we should talk about that more, Terry.
Excellent. Yes, I
Please
will.
do.
Yeah. In fact, I'll send around that paper as well. There's a.
Wait,
Hello,
Terry,
GT, go ahead.
Just one more. After Telluride, is there a way we can still communicate on to just progress on this?
Yes. Oh, that's actually a really good point. So the Slack channel will be staying open. I'm still involved in conversations from last year's Telluride through the Slack channel. So so that'll be the main way that'll happen. Shichi, you had your hand up. Or, you're muted though.
I was going to say there's a reason why people don't build dendrites. It's because of the chip area, right? It's nice to put these different compartments, right, associated with a neuron, but by the time you put that all in the same chip area, you get much fewer neurons. And so then you have to show some kind of computation that you gain by using these dendritic compartments over not using dendritic compartments, because you probably could solve the problem by having a bunch of neurons, right? Like many more neurons solve the task. And it's kind of this thing that makes it difficult to just continually build chips with dendrites. I had a student long time, well, maybe 7 years ago, and she built like this lovely chip with a bunch of dendrites and so on. We showed that we could implement direction selective models using the dendritic compartments, having different delays and so on, right? But then you have to ask yourself, could you do the same thing by using neurons alone, right, without dendritic compartments? So it's really finding the right thing, right, that you can demonstrate the usefulness of these compartments. That's why it hasn't been really built as much. I mean, the circuits are there, right? If you really want to build a chip with compartments, I'm sure, like Jen, even your students can put one together. Well, I think it's showing what's possible.
Right, we've done it several times.
Yeah, right. So it's
And-
just showing what you can do with a chip with, I mean, yeah, you know what I mean, right?
Right. And there have been some clear advantages on that. And arguably the biggest thing for dendrites, if you look at it closely from a hardware perspective, is the amount of capacitance you need to drive going between one sort of neighboring compartment to the other is a lot smaller than having a whole neuron having actually then create action potentials and firing out. And that's fundamentally where it comes down to, but it really makes you rethink some of the perspectives we have. So I think that's what's hard. I think it's actually less about the hardware. I think there's some good arguments there, but it's harder to think that way because it kind of forces you into very different model perspectives and puts us in an uncomfortable place in terms of our modeling.
Yeah, I think the model has to come first here. The circuits are definitely ready.
The
Right.
circuits have been ready for a while, but I think
Yes.
our understanding of the models is
Yes.
the hard part, and that's tricky.
Yeah.
Because there's a lot of inertia in certain places.
You remember this work from the guy at USC? What's his name? This is so
Bartlett?
bad. Yes, Bartlett, right.
Yeah, Bartlett's a good guy. Yeah.
Yeah, right. Maybe show that you can have the same memory capacity with dendritic compartments as like layers of neurons.
Yeah, so there's a
Right.
thought of talking about as layer of neurons, but that I think just scratches the surface. I think there's more to it than that. So
Yeah.
it's cool though. Yeah, but Bartlett's a good guy. Anyways, yeah, this what I get. I don't know if today was a dendrite discussion, but that's fun. I love doing that.
Yeah, no, the purpose of today is this is a discussion chunk, or at least this time block for today is a discussion period for the ANT group in particular. So I'm quite happy with the dendritic discussion, but the thing we would like to be focusing on in this discussion is talking about various issues about remote access to neuromorphic hardware. So I've got a couple slides to just sort of go through and say, here's how we are framing the sort of discussion. And then, so we're going to start out with that sort of thing and start opening up, continue this sort of free-form discussion. Why provide remote access to hardware? And again, please feel free to interrupt me and break in a moment. So why provide remote access? I want to play with everyone's hardware. Like there's so many fun chips out there that I just want to use. And I think there's lots of other people who feel the same way. Especially since, I mean, it is such a broad international community now, or has always been, but even more so. So it's a broad international community. I would love to be using things from other people's labs. I'm also a little bit biased there because I'm not in a lab that makes anything. I only work on the software side. So most of the time we just sort of beg and plead and borrow some pieces of hardware, but that doesn't scale particularly well. I think there's also a big thing that we've seen a couple times where expertise in designing a chip doesn't necessarily translate into expertise in using a chip. My first experience at Telluride was, I showed up with this freaking weird neural engineering framework Nengo thing, which was meant for doing cognitive brain models. And then it turned out that after talking with the Spinnaker folks, we were able to really quickly do demos on their chip that they hadn't been able to do before, just because of using this very different ways of thinking about organizing things. So that happened with Spinnaker, and then that actually happened again with Luihi. So when the Luihi crowd, when they finished developing they were in the last stages of developing their chip and wanting to go release some demos, they hired a team from the Waterloo group that had developed Nengo, and just hired them to say, all right, please make demos. So I do think there's this aspect that it's a different set of expertise, and that makes sense. And that in order to really accentuate that and let people focus on what they're good at, we need to get remote access. In-person Telluride is a wonderful first step to playing with people's hardware, but it's only accessible to people who can afford to go there. So I would like some other approach. There's a bunch of different things out there that are working in this direction of remote access, and they're wildly divergent. So that's sort of what I want to sort of wildly just quickly swing through a lot of these different approaches. So Luigi has done a really good job of integrating everything with Slurm, which is a standard tool for scheduling jobs. Basically, you log into a remote system and run your program, schedule a job. You basically say, all right, when here's what I want you to run it when the hardware is available. It's nice, well-supported, well-developed, common software. When we were playing around with that sort of stuff here, one huge disadvantage was, as the university guidelines meant that I could not set up a system like that at my institution. That just would be a wonderful thing to do. University guideline says I can't. Are there ways around that? The HBP Neuro Robotics platform is a very, very different approach, but also I think really worth noting in this community. I mean, initially it was designed more for, hey, here's a simulated environment. Here's a big giant supercomputers to run things on. Download this local VM so you can do a sort of a local simulation of what would be happening on the large hardware. And then once you're happy with it, send it off and run it on their big hardware. Most of their emphasis is on normal sort of GPU access and CPU type things, but they do have an interface to Spinnaker, and they've been talking about interfaces to Luigi. And they've done a really good job of making this sort of thing accessible to all researchers. It is an extremely complex piece of software. And it is also a situation where they're hosting the hardware, unfortunately. But it might be a situation where with a fair bit of effort, one could get one's hardware added to their stack. Jennifer Hasler has a really nice system for the FPAAs about where you literally you have a local VM that virtual machine where you make up your simulation, you build up the model of what you want to run, and then you literally send it to an email address. And Sejnowski, goes ahead and grabs that email, runs the model, and emails you back the results. Really nice in terms of democratizing, everyone can access this. There's no accounts needed. I'll assume if it becomes really, really popular, you might add in some sort of access control. But that's one of those problems that it would be nice to have. And it is custom software. I mean, it's open source custom software, but it's not as standard as a lot of other things. Is there anything you wanted to add on that, Jennifer, before I go on to the next one?
There's a whole bunch of things I can add, but I'll let you finish, and then I'll get the next. I'll color it.
Perfect. There is another approach, the sort of the minimalist approach of, just let people SSH into your computer, which is a lot of, it's the same setup that a lot of us are using from home. So that's got the nice thing of, you often don't have to set up anything extra. There's, you can create accounts or guest accounts. This is, of course, as a minimal option. I've used this a number of times for accessing remote hardware. Security can be tricky. Multiple user access control to the hardware can be really tricky, and that sort of thing. But it is, I do think it's worth thinking about. Is just sort of, look, this is minimal, and it's something that is often already set up. Are there ways that we could make it a little bit better? I will also say a couple other things that I've found sort of practical concerns when I've used a number of these different approaches. Being able to reset the hardware is really, really, really useful, especially when so much of the time this is prototype hardware.
I will second that. You'd be surprised when you really use them, how often that happens, how much you need to do a reset.
When we were working with Luigi, we set up, you can do power supplies. You can also, remotely access the power supply and tell the power supply to cycle everything. Really important, and ended up being something we used quite often.
Mhm.
So that's, very shocked at how often we need to do that. It actually got a little bit more complicated even with something with like Braindrop, where in sort of the initial versions of that, it ended up being in some situations fairly temperature sensitive. So we also ended up doing sort of remote control of climate control sort of things. That was kind of fun. Also, because again, this hardware tends to be in a state of flux and in a state of, people doing updates and things like that. I get sort of used to when I'm working with hardware, oh, okay, I know what's going on. I'm making changes to things. And then I know that the software has been updated. But again, these were things that would happen sometimes with Braindrop is that people would update the firmware a little bit or do something. And then like, oh, now we got to let everybody know that these things are happening. And maintaining version control and knowing you don't have physical access to the hardware. It's hard to remember, oh, is this the one that I upgraded the firmware on, or is this a different one? So that was important. And then I think there's also this aspect of now and then when I'm running sort of data for, I'm gathering data for a paper or things like that, I really do need to say, look, I want sole access to this thing right now. I'm locking everyone else out. I think those sorts of issues. I think that's all I had. Jen,
do we want Jeff to actually talk a little bit, and then I can end it.
Yeah, I have all the answers. No, I'm just kidding.
I think Jeff presents a unique perspective, and then I'll color it with at least my experiences.
I have more and different questions maybe. So
good.
We've thought about a few things. So I'll just share. Is it okay if I share a few slides?
Please.
Yeah.
Okay. So just as background, along with Jen, I help run a testbed. This recently been funded as an NSF testbed called the Rose Gallery, and this sits at Georgia Tech. But it's got a bunch of different things in it, and we've thought about a few of these questions. I'm not going to say I have all the answers, but we have some thoughts on how you might approach some of these things. So in addition to Terry's questions and Jennifer's questions, there are a couple of things that we've thought about that kind of apply to a bunch of different prototype hardwares. And so, what I think about when I say was challenging about remote access, it's things like how do we kind of deploy environments, tool environments? Again, how do we share some of these very scarce resources? How do we remotely power cycle and debug stuff? And how do we kind of get people started is one of the big questions, especially if some of these things are more challenging. And then I have a couple other software questions. Is everything just a Python notebook? I think the answer right now is yes, but I'm open to discussion and debate or something like that. So just to tell you a little bit about the testbed we have, one of the things I think that makes it amenable to remote access is that we have kind of a disaggregated testbed. So on the left-hand side here, we have our campus map, and we actually have, our hardware's on these different stars. It actually sits in different data centers and different buildings. I have an FPA and that Jennifer kindly donated to the testbed, and actually right now it sits on my desk. I need to move it, but you can SSH into it currently. But this top thing is kind of the most important thing. You have something that looks kind of like an HPC cluster, but we have all these gray things, which are VMs. So those are, software OS tool resources that sit anywhere. And then we have all these hardware things that are blue. So we have, like here, we have FPA host is some of the neuromorphic hardware that we currently have deployed. To take it up, another level, to abstract it a little bit more, we drew this nice figure for our UNICEF grant, and you said, of course, obviously there's all this interesting hardware. FPA, I think, is one of the key ones that we want to deploy at larger scale. But there's all this important other stuff that goes along with it. So there's like tutorials, training materials. How do we tie in with resources that people know how to use? So, it's not just the hardware. I guess there's software, there's administration, there's all those other things. So here's kind of my idea and vision to help try to think about how we're thinking about some of these. And we haven't done this at scale for FBA, but this is where we're really hoping that some of the folks here can, be engaged, and especially as you're using things and saying, hey, I really want to do this, then that gives us more motivation to more quickly deploy stuff. But we have a couple kind of principles of how we want to do remote workflow, and I think it's sort of an amalgamation of some of the different techniques that Terry suggested. So we have kind of VMs that we host that have things like Ningo, that have the RAS tool set for the FDAs. So you can kind of develop, simulate, and emulate, in a kind of scalable resource. So VMs are things that we can kind of replicate, and we can add more memory to, we can add more cores to, in a way that's a little bit more scalable than, if we say, hey, please download the software and run it. That works on a small scale, but at a certain point, if we're talking about doing some of these, maybe we're looking at some of these really big dendritic designs or something like that, then we really need to scale up the resources that we have to simulate those. So that's kind of the key, the first step. The second one, I think, is standardized with what Intel and others are doing, is you have to have some kind of scheduling. So we're kind of trying to get this up right now. But this provides a lot of things. This lets you have the sole access to hardware. This lets you know who's using which hardware. So, it lets you get statistics on, okay, so, Terry used, this device for 2 days this week for 3 hours a day. And maybe that means I need more of this hardware or more of this software resource. And then it's also nice too, if you're running one of these stuff projects, to point and say, hey, look, people are using this. And then the other kind of key piece that we have that I think it's not really, I haven't heard mentioned a lot, is that you have to have kind of the shared concept of backend resources. So I don't know that we've gotten any data sets that are super large yet for neuromorphic hardware, but what we've seen for some of our other infrastructure is that we really want for all our data and all our designs to be kind of easily accessible. So we have these VMs. Mm-hmm. These live in one data center. Then we have this Raspberry Pi host connected to an FPA. So this is actually the one that's on my desk right now, this picture of that. This is in a different building, but we want to be able to kind of seamlessly share, the input data sets, the output, and then the designs that we want to program onto the board. So these two right here are kind of where we're at right now. We have this, I think we want to scale up the number and type of devices we have. But the key thing here is you can't really schedule an FPAA, so you have to pick something else that is usable, accessible, and that you can run. So if we're using Slurm, you have to be able to run Slurm on it. So this Raspberry Pi is a $50 board. Obviously, we don't necessarily want to compile really large, we don't want to run really large Ningo simulations. or do our full compilation there, but we do want it to help us kind of access, control, and manage the interaction with the hardware. On the right-hand side here, we have, what Terry mentioned, this idea of a remotely addressable power strips and power bricks. We ran a class that used some pink FPGAs, and we found this again is critical. You have to be able to power cycle some of these devices, because even if they're connected to a Raspberry Pi, you can turn off the USB power and turn it back on, but the device will kind of get in a weird state if you do that a lot of times, especially for FPGAs. So you have to have some of this other backend stuff to kind of support that. So just to kind of quickly answer some of my questions, and I'll post some of these in the Slack as well. I think we have a few approaches. I don't know if they're the best approaches, and I'd be really happy to hear feedback. I think the things that are toughest that we haven't figured out how to solve are debugging. That picture I showed previously, you could put a logic analyzer and just leave it on, say, the FPGA. But is that scalable? Is that easily usable? I don't know. The other big challenge is, for us, we're an open access testbed. Pretty much anybody in the US and Europe and most of Asia can request accounts. But NDA hardware is really hard for us to host, and I think even for say like low E, it's tough to figure out how do you publish and how do you with a lot of these you want to build a community, and it's really hard to do that with certain types of NDA hardware. So that's my spiel, and just to briefly advertise, we do have. You can request an account for our test bed. So, we're kind of working to set everything up, but hopefully some of the AMP subthread folks will be interested, and feel free to reach out to me. And I'm happy to hear everyone's thoughts and feedback.
Cool.
Great.
So,
Jennifer, do you want to close us off? Or?
I can grab the screen in a second.
Yep.
By the way, Jeff, thank you for all of that. That was very helpful.
Oh, you're welcome.
Let me share my screen. I'll do my PowerPoint. Which one was better? Cool. And a couple of things to look at there. So we've been looking at this sort of remote system for FPAs for a bit. What has been helpful for obviously for those who remember from previous things and talks, is that there's a whole infrastructure around this, and some of you who've been playing in the Ant group have go, oh wait, we've talked about various aspects, and there's a lot more to talk about. But there's been a whole major sense of building tools that allow us to build, sort of taking sort of, high level sort of things sitting in a single virtual machine that we can like take blocks, pull them together, and then actually, compile them either for sort of simulation or hardware. And because it is floating gate based, but because all the programming is done on chip and all of that's, has a pretty straightforward flow to it now, we just kind of feed data to it in a program, in a certain controlled way, and it programs it. That gives us some opportunities. And so then we start asking, well, including we've done Android, we've even had some simple test structures on Android. It's been kind of fun. But then it came to questions like, well, how do we handle doing this remotely? And so there's a whole remote system that we've kind of looked at this. And the genesis of this was, I remember actually just before going to Capocaccio, I was visiting a good friend and colleague of mine who's Mark Smith, who's up at KTH in Sweden, and was talking. We were kind of, he's a master builder in terms of hardware and other sort of things, and really great person there. And really wanted to, he's like, hey, it'd be great, all these FPAs are great, but I'd really like to get access to this. And I kind of saying, well, okay, we could talk about figure out how to do boards and other things. And this comment was like sort of this offhanded comment, which was like, well, why don't you just like stick it on an email server and do something? And I went, huh, that's actually a good idea. Why was that such a good idea in the, and we're like, and then that sort of became the core structure. Why did it become such a good idea? Because I didn't have to worry about any infrastructure issues because being at Georgia Tech, although of course Jeff has nice access being in the CS department of certain things and can control on it, most of us don't actually get to do anything. And we're all kind of told, no, you can't run any automated structures or anything else on there. Like, oh, that's unfortunate. And so what do you do? Well, wait, I can put an email system because nobody can stop me doing that, right? So, and we found out that that's actually much more powerful than we ever expected in the whole space. The other view was, let's be able to take the tool structure that we have, kind of in a cartoon version here, and be able to use the same tools that we already use for, if I had a board sitting in front of me, like in my system plugged into a USB port, so all the boards are USB powered, USB controlled, and be able to just add another button, which is the idea, that could just get sent to some email address in the cloud that sits in the email. It's a Gmail account. And then we have a system sitting there just going, oh, I'll just like look for the email, pop it off, take that email, and then be able to take the result. Now, by the way, you actually use your tools to compile it. So you're using your tools to do everything you would have done otherwise, except when it comes time to target the device, you instead send email and send it across. Okay. And so it gets to this remote system. It goes, oh, okay, I've got the entire structure. Let me just download that into the FBA, basically target it, set up the registers, program, so that way, and then set it running. It runs. Once it's done running, it pulls all the data out and goes from there. And because everything can be self-contained through the USB, that works out really well. It then packages up everything that in the structures that you would have defined in the SRAM, packages it all up and sends it out through email to your base machine, and then you could load it back up into the same tools or do something else with it. So it's kind of an interesting perspective. It does work, which is actually, works fairly well. It does require the way we've approached it to keep everything all on chip. And this was actually intellectually a good thing for all the FPA designs, because for a while we were having a lot of students think, oh, I'll take my chip and then I'll have a rack of equipment and test things with it. And what you begin to realize is, no, actually the chip is your test structure too. And so how did you begin to think about that? And so part of that was, how do I begin to think about things where I have, in this case, there is a processor on chip, because why not? And SRAM memory, which by the way, memory is the expensive part on this chip per area. That's an interesting architecture question in and of its own. But all of the analog and digital blocks, and you can kind of integrate things into it such that you don't just think about the blocks you're testing as your system, but the whole thing is your system, including all the mixed signal structure. Became really, really important intellectually to do that. But then you could take something and say, just do a simple low pass filter, and lo and behold, input, DAC input, and then this is what comes out of the memory. So it works out pretty well. And you can do even more complex things. By the way, our code typically has this graphical nature. It's one data flow where you can actually say, oh, let me take 6 bandpass filters and run them, and then put in a chirp input and then amplitude detect, which is also done on chip. And then do ramp ADC. We scan and put in ramp ADC, and that gets put into SRAM. And you can actually see the peaks that come out of those structures. A very simple measurement, but it's just kind of a fun one to look at. This became really important for many, many reasons, because we have a very strong belief in bringing hardware into the classroom. This has its roots, and some of the people listening will remember, the days of Caltech, where we believe very strongly in, say, for a CNS 182, the analog VLSI class, that people would be doing measurements every week. I guess I still believe that. I still believe in doing heavy amount of measurements in class. It really helps both the class and the research, much the same way it did, 30 years ago. And so the same kind of structure there. And then to say, well, okay, well, if I have a remote system, that really complements the ability to say, okay, maybe I can provide some boards for students and they can come with a laptop and hook it up. And so that's a very nice, straightforward thing in these kinds of configurations, but it then also allows me to have a remote system allowed for the students. And we were doing this pre-pandemic, we were starting to do this pretty heavily for classes in 2016, 2015 and 2016, as we were bringing up some of the newer devices. And that turned out to be huge. And again, you can get a sense, this was sort of class topics that we used for an analog VLSI class, and some of the things that people actually did, some of which were on remote systems. We ended up doing this as an undergraduate class, and because of some weird administrative problems, we couldn't actually get the lab space to put the boards anywhere for the students to use them. So they had to use it entirely remote. And it still worked out to be fairly positive. In fact, one of the things in some surveys that I actually had them do, they really, the first undergraduate sort of transistor circuit course, they really believed right from the beginning that experimental measurements were important for learning circuit design, which I think is just a real fundamental shift to the way people looked at things. So that was really cool. What was also really fun is we could get some interesting data analytics on when students are actually working. This was quite useful for us because we were able to figure out when the project deadlines were and when the use would happen. And you could see that there's always some interesting bursts a few days before something was due. We could also see right after, around an exam by other users. You could always have students, in particular right before the third exam, say, oh yeah, we're working really hard on this. And I could look at the system and go, well, that's funny. I don't see much. Maybe we should communicate about this. And so this was kind of a neat thing that came out of that. So it really was kind of cool. And actually, by the way, doing it just allowed us to transform the way we taught sort of that analog design, which actually allowed us to be much more system heavy. Everything wasn't about building an audio amp all the way through. So we had a lot of fun with that. And created a lot of conversations, both during the class and afterwards, a lot of conversations that even would occasionally, diverge into discussions over beverages in the evening, but it was great fun. So these are the things that start happening as you start putting it together. And it was a really simple concept. And I'll be the first to say there were, it's not always perfect, but by the way, having that reset was really important. We reset our system all the time because it's amazing to find ways that students could kill something that we didn't realize could be killed. And then you go in and you clean it up. But yeah, it was very useful. So I will stop there. And I'm happy to talk more about it. But hopefully I give just a single perspective on how we were playing with it.
Great, thank you. Cool, so that's our experiences with remote access. Anyone want to step in and add to the conversation?
Yeah.
Well, I want to just, hi, nice summary of what's going on, and very good intro to the whole field. I think you've forgotten the True North.
Oh, right, yeah, I never even got used to
that. Was really quite, it was quite used at Telluride. And the model there was the SSH, and that, you have a bank of machines, boards in a system, and you SSH. I think this is also what Intel did at the beginning before they went to more sophisticated things. So the question I had is that, so are we going to try to come up with a scheme where anybody that has some kind of a hardware to share can put it in the back end and then we can share it?
I think that's a goal to work towards. I think there's going to be a couple of different levels of that. Like if we can come up with good tips of, look, I just want to do something minimal. What's the minimal thing I could do? I think that would be one interesting thing. I think there would also be, okay, here, what would be best practices if you want to do something serious? And yeah, that's what I would hope for.
And there may be cases where they could be hosted in different, in central places if we wanted to do it, although certainly distributed has its own advantages as well. But I think if we could get multiple kinds of hardware up and then people could try different kinds of hardware and compare, and I think that would accelerate a lot of the conversations in this field. And probably encourage people to build more hardware, more interesting stuff too.
So also I want to say that if you also take the HTPU, the Google HTPU, the model that they use there, they have a Raspberry Pi basically front end, and you SSH to the Raspberry Pi running their own Ubuntu. So I think that may be, and I think that's what you're doing too, Jennifer. I saw the other Raspberry Pi.
Well, we're actually not doing an SSH. It's actually just a straight email structure.
Yeah, that's kind of what we're doing with our FPA. But I think
with what Jeff is still doing with his at the moment.
I think that's, you know, to me the Raspberry Pi is important for things that that, you know, so obviously in Jennifer's case, you know, they have this email server and there's a system and it's connected to the FPAA. So it's kind of like, I think they're the key thing maybe you're pointing at is that maybe we should standardize on, okay, there are a couple of different approaches. Like one is, okay, I have one of these and I have one machine. Maybe I set up something like the email server, and then that kind of provides access, you know, kind of
yeah, but I think right. But so the mail server versus SSH are at two different, they're at the same level, and the Raspberry Pi is an interface, it's a low-level interface to run those.
Sure.
And also the other question that I want to say is that we are, so far the discussion has not involved anything that is related to sensory motor integration and real-time control. And that is the $1 million question, I think, that we need to address.
That is a really good point, that all of this remote access stuff right now, we're looking at situations where you can either here's a pre-computed set of inputs that I'm going to use, or here's a little program that I want you to run on the hardware that'll generate on the fly what I want it to do. That's, yeah, I don't even know even to think about is that just a fundamental limitation of remote access?
I don't think it's a fundamental limitation, but what I think it requires is asking, you know, okay, say we have a really good sensory motor system that we want to build or look at or do something with. Obviously, we would need to have that entire remote structure platform put together. So now we're not just talking about here's a hardware board, but we really would need to say here's a hardware board sitting on a device that has, let's say, in a robot platform. For example, we have a few of those at Georgia Tech, and I'm other lots of around, and they would sit there, and then you could actually, interact with it in some way, have it operate autonomously, see what you pulled out, and then bring it back. Certainly believable to do it. It now requires, though, that if you had a collaboration between a couple people to build a physical system, you could do that. I don't think the view of saying, here's a remote system, and then I'm going to run the whole thing over the cloud to the other system is probably what we want to be doing. But, sure, that's at least a conversation point.
Yeah, I agree. I think you could see having like a DVS camera set up with something, maybe some interesting inputs connected to some hardware, but you can't, I just don't think there's any way that we can easily say, okay, let's decouple those and have the sensor, the input be in one place and then, stream that data to one of these devices, at least not with all the, I mean, it's tough enough to get this to work remotely if everything's together. So that's kind of the key thing.
Isn't Address event-based representation a means for doing that? Right, that was one of the main premises of the address event representation, right? To be able to communicate between chips that are totally different in what they do.
Yes, Gerd, it was. Although there were two things, right? One was have a sparse output and the standard communication.
Mhm.
Of course, you got to get the first one to make the second one work.
Yeah, so the second one is the important aspect of reconfigurability, that you can interface sensors and processors right, in a modular way. Right?
Yeah.
The aspect that actually was, I think, the biggest stumbling block for me was, I actually have been doing a bunch of situations lately where I need remote access to DVS devices, and it's actually been more like, oh, it's not just I need remote access to the DVS, I also need remote access to whatever it is that I'm waving in front of the DVS in order to change my stimulus how I want to do it. And that's actually been the more complicated thing for setting up one of the test benches that we're working on right now. It's like setting up a bunch of propeller blades and I can control the speed at which they're spinning at, or LEDs that I can control that are sitting in their visual field. Actually, one of the biggest stumbling blocks we hit is that we suddenly realized, shoot, I want to be able to do remote access and adjust the focal plane. That's tricky, or at least with the lenses we were using. We're like, oh, shoot, didn't even think about this problem. So for us right now, it's actually been more about how do we get remote access to the environment that we're pointing the sensor at?
Yeah, good point.
Gert, do you want to say a little bit about what we're building?
Sure, yes. And in fact, one aspect that I think we really need to address as a community is not just the excitement of hardware, which we all share, right? And I think it's almost an insider's endeavor here, right? So we all are enthusiastic about hardware. And of course, we like to see, we like everyone to have access to our hardware. But so the challenge is that while we think hardware is great, that's not necessarily the case in the broader neuroscience community, right? And so Kwabena, when he started the Neurogrid, right, he had great aspirations for making this a tool for computational neuroscience, but it has been hard really to have computational neuroscience scientists subscribe to this. Sejnowski is one notable counterexample. Of course, he's very much into neuromorphic engineering. But the broader computational neuroscience community has been very reluctant to get into hardware at all, even digital hardware, right? And hardware has all these challenges, which interestingly, those are very good challenges to have from a neuroscience perspective, because neuroscience is noisy, is highly variable, and so you would think that a neuroscientist would want to have an experimental platform to try out those aspects, right? But it has been perhaps an uphill battle in the community. Also, traditional AI can't care less about analog hardware. Typically, I mean, from the very beginning, it has been more of a digital endeavor. But yes, so the challenge is there to engage the broader community as much as this to make our hardware accessible to the community. And one first step, and we have also experienced this, so clear now with the workshop we have here on neuromodulation control. Sure, you can have your hardware with many bells and whistles of all control parameters, thousands of parameters. But a traditional computer scientist would expect the hardware to do exactly what you want to do. And you give it its parameters and you get exactly the same, right? You run it twice, you get the same answer. That's not true for neuromorphic hardware. For analog hardware, that's not true, right? And so you have to deal with all this noise and variability. And so we need to, so we can't just throw this at the community, the computer science community. We need to also address the, how do you make this robust? How do you make this programmable in a way that you can make it run, right? Reliably, right? And it's a hard challenge.
Can I show a couple of slides, Gert?
Yes, Steve, please go ahead. Yes.
Well, we're working with the. Can you all see my screen?
Yes. No.
Yep.
Okay. We're working with the Neuroscience Gateway through the Supercomputer Center on campus, and they have built an infrastructure that allows people who have access to this supercomputer center nationwide, if not worldwide. I'm not sure where the limits are. They get an account, they can run simulations of all sorts of neural models and all sorts of packages. It's quite a facility for software emulation. And what we intend to do is attach something to it. If I can bring this up. I hope you can see this. You see something that looks like a rack of equipment?
Mm-hmm.
Okay. We're going to attach something to it which will allow emulation of spiking neural networks. This is a work in progress. It's not ready yet. The hardware pieces are put together, but it's not rack mounted yet and attached to their system yet. But basically you have 5 or 6 servers here, and 5 of them will provide emulation. When it's all done, we hope we get to 160 million neurons and 40 billion synapses, because there's 8 Xilinx FPGAs in each server, each having high bandwidth memory. So we can emulate neurons very rapidly with cores in each of those FPGAs. The processors in the racks are dual EPIC 32-core processors, pretty much state of the art, and about a half a terabyte for each of those processors, 25 terabytes of solid state NVMe storage in each server. So it's quite a powerful server system. Now we just have to get all the firmware and software up and running and attach it to this gateway so people can run spiking neural network emulations. Anything you want to add, Gert?
Yeah, thanks, Steve. So this is a preview, right? So we're in our 3rd year of this NSF size resource infrastructure endeavor, right? So this is computing, information sciences, engineering directorate resource infrastructure for the community. So here we envision a system that caters both to a computational neuroscientist and to an AI aficionado, right? So sliding between artificial intelligence and neuroscience theory. And this being fully reconfigurable. And also, well, we like to be trainable. So the trainable aspect is something that we're still grappling with. But so we have now some pilots, right, where we have a few nodes of that working, right, where we have this high throughput reconfigurable neural computation that is hierarchically structured, right? So any neuron can connect to any other neuron in the architecture with scalable bandwidth, scalable communication. It's a high bandwidth communication, and we want to harness the high bandwidth memory as a means for doing massive throughput in neural computation. Right? But so the as I was saying, so the main challenge here is to how do you make this of interest to the neuroscience community and to the AI community, and that's the hard part. I mean, so the hardware in a way is not the easy part, but the hard part is really to make this user interface friendly and usable for the community. And so here too we have Python interfaces that we're developing. We're also now, so this Neurosciences Gateway is a very nice tool for accessing supercomputers, but accessing a rack of FPGAs is not trivial. And so Terry and January pointed out some of the difficulties there, right? How do you have a computer scientist interface to all that? But we have a pipeline. So with Emmer-Nefzi, right, we developed this interfaces going from a PyTorch formulation, say, of an AI problem into a spiking representation, and then from a spiking-based representation go into we have a set of compilers that go from the network that has been compiled from the AI representations into now the hardware. and doing the sufficient partitioning of your network, hierarchical network, across the entire system here. So Steve has been really instrumental of putting together the system with a large team, and we'll have a big announcement later. I didn't mean to make this. So Steve, I think you can say more, but so we'll give a big announcement later once it's all up and running. But so right now it's almost to the point where we have small pilots ready for people like Espoir here, who has been from companies that have been trying it out.
I just mentioned it in the context of people were wondering how to submit jobs and so on. And Neuroscience Gateway has the skids grease, so to speak, for submitting jobs through their system. And we'll be running Slurm on our end so that we can accept jobs coming from them that will be pre-configured based on these tools that Gert mentioned. And then we can assign resources through Slurm to run the job and send the results back. So it's a similar approach to what was being described.
I would like to bring this to Telluride in next years, right? Yeah. And very much look forward to coupling it to Nengo and all those other great tools. Yeah.
So, Gerd, what happened? You're going FPGAs and digital VLSI for Neuron?
Well, we sent a $2 million proposal to NSF and they cut it down. So we had to get rid of all the chips. But yeah, it's just FPGAs. But in a way, it's a first step. And actually, if you look at bandwidth, it's hard to beat one of those Xilinx UltraScale Plus FPGAs.
Yes,
with
it is difficult.
400 gigabytes per second memory bandwidth.
Unless you build your own chip.
Exactly. Every chip gives us 100 giga spikes per second, 100 giga synaptic events per second. It's hard to do, hard to beat with analog hardware. Yeah.
All right. With that note, we should probably wrap things up because we've got Terry Sejnowski starting in a moment. Is there any last things you want to say, Jennifer? Or?
I think we're good. I really enjoyed this conversation, and I think hopefully the thing that's important is everyone realizes that this is probably something we're going to continue to keep talking about over the next couple of years, I'm sure, one way or the other. So I really enjoyed the conversation.
Yeah, let me also thank Jen for putting hardware on the network and giving access. That's great. Yeah.
You're welcome. Thanks. Thanks, everyone. Now everyone gets a 2-minute break.
Yep. And Terry, you're all set to present in? Or...
I am ready to go.
Sounds
I will
good.
share the screen and get things going. Let's see. Here we go.
Seems to be working. Not full screen yet. Yes, now it's full screen. Perfect.
Okay. Well, look, I will launch as soon as you give the signal.
Sounds good. We'll give people another.
Yeah, they need a bio break.
Yeah, exactly. I'm so bad about giving people breaks. I just forget. When I run the Nengo Summer School, I have found myself, oh wow, I just talked for 4 hours and I didn't give anyone a break. I'm sorry.
Well, you remind me of the neurosurgeons who pride themselves on 12-hour operations without going to the bathroom.
Oh, that's scary. Oh.
They should come up with something like the astronauts have, right? Where you don't have to leave the room to go to the bathroom.
I was going to say the surgeons can insert their own catheter and wear a leg bag if they have to.
Well, beyond the call of duty, I would say.
Just as a reminder, everyone, this is being live streamed and recorded. Be careful.
Oh, my goodness. Okay, well.
It looks like the bio break is over. We're now at, I guess, 10 o'clock Mountain Time. And Terry doesn't really need an introduction. He has been integral with the neuromorphic community from the very beginning, right? Telluride. In fact, also is has been part of the very first Telluride workshop, and also has been a father of computational neuroscience. So everyone knows him, and so. But this is going to be another segue into the neuromodulation control group, and so we'll have so after Eve Marder's talk and also Todd Coleman's talk on very complementary perspectives. So now we're diving into neuroscience with looking at how neuromodulation can actually multiplex networks in the brain. Very exciting work. So Terry, give it away.
Well, great. This has been a great workshop. By the way, the last time someone introduced me by saying that Terry doesn't need an introduction, he continued by saying, well, let me tell you a little bit about myself. And so, but the workshop, you're right, Gert, it really has taken on a life of its own. We started it, 27 years ago. And I think it's now the time has come, and it's really exciting time. So neuromodulation. Not everybody here may know the history of how neuromodulators were discovered. And so I'm going to start with a very brief history of the person here who discovered the first neuromodulator. His name is Otto Loewi, he's German. And he did an experiment, a classic experiment in 1920, which won him the Nobel Prize, by the way. And it was at a time when, in fact, it was controversial whether or not there was chemical transmitters between neurons or whether there was electrical. And this was very contentious. And it was very difficult to prove. And so he did the following experiment. What he did was he stimulated the vagus nerve of a frog, which was known to slow down the heart. And he perfused the heart and collected the perfusate and then applied it to the heart of a second frog. And sure enough, it slowed the heart of the second frog. And he didn't know what it was, but he knew there was something in the perfusate. He called it Vagus. You could imagine why. And subsequently, it became was purified, and it was acetylcholine, which is a neuromodulator. He also, by the way, discovered another neuromodulator which speeds up the heart, adrenaline. So, and these are now known to be two very important players in the neuromodulatory modulation of the brain. By the way, acetylcholine acts both as a neuromodulator and as a direct neurotransmitter. It's at the neuromuscular junction. It is responsible for activating muscles. Now, I had an encounter with Otto Loewi, of all places, at Woods Hole. So I was walking with Stephen Kuffler, who was I was a postdoc at the time working in his group at Woods Hole. And we walked by this church on the way to the lighthouse, and he said, "Oh, do you know that Otto Loewi is buried here in the graveyard you can see behind there?" And I said, "It's amazing, Otto Loewi. He's kind of like 100 years ago." And he said, "Oh yeah, let me show you." And so he took me to his grave. There it is. Otto Loewi is buried at Woods Hole. And this was a kind of a connection that really is the sort of thing that happens across many generations. Through Stephen Kuffler knew about this, and Otto, apparently, he told me a story. Loved Woods Hole, and he would come there in the summers, like many scientists from around the world who gather there in the summer. Okay, so we heard a fantastic lecture by Eve Marder last week, in fact. And if you didn't hear it, what was remarkable, at least from my perspective, was that this little stomatic gastric ganglion, which is in the middle here, with 30 neurons, has on the order of 2 or 3 dozen neuromodulators, right? Just this little ganglion. And these neuromodulators are able to do two things. First of all, to reconfigure the network to have different functions, but second of all, to help the network become robust. That is to say, through changes in temperature, changes in the stomach, what the lobster happens to eat, crayfish in general, and and for example, there's two different rhythms. There's a gastric mill and a pyloric mill, and they differ in their frequency by order of magnitude. and the way that you shift between the two is through neuromodulation, which changes the strengths of the synapses and also the ionic currents, the properties, intrinsic properties of single neurons. And you know, this is in an invertebrate, but in fact, the very same principles apply to mammalian brains and specifically to human brains. I mentioned acetylcholine. Well, acetylcholine is a very important neuromodulator. Acetylcholine is important for regulating attention, for example, in the awake brain. And it is also important for regulating rapid eye movement sleep, dream sleep in sleeping brains. Now, here are three other neuromodulators, which you've heard about. Dopamine, which regulates many different forms of behavior. The phasic bursts of activity in the dopamine neurons regulate plasticity, synaptic plasticity during reinforcement learning. And also the tonic level regulates the motivational state of the brain, how motivated you are to take an action or not, depending on the rate of firing, background rate of firing. And dopamine, in fact, is also responsible for addiction, for all addictive drugs act by increasing dopamine activity. Adrenaline, as I already mentioned, is important for activating the brain. So it's active specifically during surprise, when you are something unexpected. And there are drugs that increase the activity of noradrenaline, and specifically Ritalin, which is prescribed for ADHD, attention deficit hyperactivity disorder, taken by millions of children. And then finally, serotonin. I'm just 3 out of dozens, but serotonin is particularly interesting from the perspective of regulating social cognition. And it is very important also for regulating sleep. And it is serotonin reuptake inhibitors, which increase serotonin activity, is used for treating depression. So we can see that these neuromodulators are really important, not just for the normal function of the brain, but when the brain is disrupted through various problems with the circuits. Neuromodulators are the target for a lot of the drugs that are used, that are prescribed. Okay, I want to give an example. This is the equivalent of what happens when, as Eve Marder does in an experiment, puts a neuromodulator into a bath with it that is now activating these rhythms in vitro preparation, where you dissect out the somatic gastric ganglion. So this is an experiment that was done in Carl Deiseroth's lab. And the experiment consisted of training a mouse to distinguish between two different odors, ethyl acetate and 2-pentanone. Okay, now it was trained to lick when the ethyl acetate was presented, as you can see here, for a second, and not to lick when the other odor was given. And you can see here on the bottom left that each one of these is a trial, and this is after the animal's been trained, and this is a water deprived animal, so it's very, very motivated to lick when there's the go cue. And you can see that there's a licking that occurs immediately after the odor is given, and it continues for several hundred trials, and then it stops. Why? Because the animal is sated. And you can see the average activity here on the middle, and you can see that the animal is trained so that very few responses to the no-go. And you can see that here for individual trials. Now, what Carl and his lab did was to record simultaneously from tens of thousands of neurons in several dozen areas of the mouse brain during this behavior And this is a summary. And you can see all of the areas here that he recorded from. The sensory areas, the olfactory bulb, a piriform cortex, and then somatosensory areas, thalamic areas, hypothalamus. There's regions in the hypothalamus that regulate thirst. And then the hippocampus striatum, the cortex. This pretty much covers a very broad range. And I want to focus here at the beginning on the right, just to show you the very broad changes that occur. First of all, let's start with the sated brain, presumably the normal condition. And what I'm showing here is the background firing rate, spontaneous firing rate in the normal, and this organized, it's ordered according to the firing rate, where the firing rate, as you can see here, varies across these neurons. But when the animal is thirsty, look at the change. It changes from high to low and low to high. In fact, almost every neuron in the brain apparently is being affected by the thirsty state, and that's because there is a hormone, angiotensin, which splashes through the brain and activates a lot of the circuits. And here now, in very great detail, is the firing rates of the neurons in the thirsty brain here on the left for go and no go, and here is in the sated brain. And just to point out that, if you just look at the activity here, this is the response to the odor, and the go odor activates an enormous number of neurons. And you can see here, in red, the ones that are firing at a high rate, ordered according to the latency. And you can see that there are some neurons that go down in firing rate in the olfactory bulb. And similar here, not too surprising, because this is distinguishing between the odors. And the no-go produces the odor produces some activity here, but very much less. Now, what's interesting is that if you go look at the sated brain, the no-go doesn't change very much. It's indifferent. But you can see that the go odor, even though it's behaviorally significant, doesn't activate the brain nearly as much. In fact, it's very similar to the no-go. So we're talking here about really reconfiguring an enormous amount of activity throughout the brain. And this is very typical of these major brain changes, and especially when you fall asleep, the neuromodulatory system completely shifts, and the neurons, new ion channels are activated, others are shut down. The strengths of the synapses are changed. This is enormously, the changes are dramatic. And I have to say that it really flies in the face of the idea that, well, the network in the brain is fixed, and there's slow changes in the plasticity, but there's pretty much the strengths of the connections between them are more or less the same. No, nothing could be farther from the truth. No, the reality is that they're always being reconfigured according to the task at hand. So I want to tell you the story now about a project that we did, and this is published in bioRxiv. Has been submitted, but hasn't been published yet. And it tries to get what's going on perhaps in a network when you see an animal that has to decide whether to approach or avoid a new food substance. And depending on the hunger level, it may approach, even though there may be a risk. And so here it is. Here's the go, no-go task. If there's a food item, the stimulus is there, and the answer, the question is whether the output is to go or no go. And here's now what we did. What we did was we trained a recurrent neural network using modern backprop techniques with 200 neurons. And we had two conditions, one with the neuromodulator, which is shown here in blue, and one without. And what we did was we reduced the strengths of the synapses when the neuromodulator is present by a half. So that's the only difference, was 50% across the board for every synapse. And we trained it up, and sure enough, we could train it up so it could do two behaviors. It could, the stimulus can either make you go or no go. And so we can actually train the network, the same network, to do two different tasks to the very same stimulus, right? So this is something that it makes it much more flexible. It means you don't have to have two separate networks for two different behaviors. You can do the same two behaviors in the same network just by having a global neuromodulatory change. And just you can do this down at the single cell level. You can see that there's changes in activity in the two different conditions. In blue with a neuromodulator, you can see some neurons dramatically change their firing rate. Others don't change very much. So this is now can be analyzed. We can look into the network and we can ask what's going on. And here's a particular network we dissected. There are two clusters. There are 5 clusters, 2 of which are inhibitory and 3 of which are excitatory. By the way, we had 80% excitatory and 20% inhibitory neurons. And so here's the 5 and 2 are the inhibitory, and 1, 3, 4 are the excitatory. What you can see is they've segregated according to the condition of neuromodulation and stimulus. So it really is able to reconfigure itself, according to the input and the neuromodulation. Now we repeat this over and over again and found that we had different clusters, and I'll come back to this later. It's not like there's one network that solves the problem. It's many, many different combinations. One of the things that we found between the different networks was that as you vary the neuromodulation level, you can actually shift between the two different behaviors smoothly, but different neurons had different thresholds, and different networks that were trained had different thresholds. So this gives you a sense that even though the networks have the same performance at the extremes, in fact, in between, they were different. And in fact, we find that in humans. Humans often respond to drugs with that affect neuromodulators very differently. Now, it turns out that you don't have to change the strengths of all the synapses. You could decide to do it either with the excitatory or inhibitory alone, and it has roughly the same performance and the same number of trials to reach performance. We can also ask the question of, well, can you do 2 neuromodulators? And so here's 2 neuromodulators with 3 different behaviors, and it learns them perfectly. Well, how many neurons do you have to modulate? And this is important because it was originally thought that a neuromodulator, say like dopamine, activated the entire cortex, and it does, but individual dopamine neurons, in fact, have more focused target areas. So we vary the target area from 10% up to 100%, and then repeated the training. And as you can see here on the right, performance was the same regardless of whether it was all the neurons or 10%. So you could do the whole switch with just 10%, which is really remarkable. It means that you really have a fantastic amount of flexibility here. And so how many can we get into this 200 neuron network? Well, we have here we have 9. We have with 2 different inputs and the output going up or down. We have 9 different tasks that we can train the network on with 9 different subpopulations of 10%. And here's the confusion matrix, and it learned it pretty well, not perfectly, but pretty well. Fraction correct is in dark green. Okay, now we wanted to look at a behavior that was similar to the one I showed you at the beginning for the mouse, but now this is experimental data from a fly, from a Drosophila, from a group that had studied food deprivation for 1 or 2 days. First, look at the control, and this is when the fly has the behavior here is showing is extending its proboscis and to drink the sugar water, and here is varying the concentration of the sugar, and you can see that for sated fly, it in fact has a threshold of about 100 millimolar, which is actually quite a lot. But if it is sugar deprived 1 day or 2 days, the threshold goes way down, and that's quantified here on the right. We repeated the training now with 10% of the neurons. First, the equivalent of, we trained it on the equivalent of the sated fly, and then with the full neuromodulation here. So these dashed lines are the training inputs, and it nailed it. And now when we vary the neuromodulation continuously between the two, we're also able to get intermediate levels, as you can see here. So this is, showing that, in fact, we really can qualitatively at least, reproduce a complex behavior. But now we can go into the network, we can figure out, what's going on. And this is the real strength of being able to create these recurrent neural networks that have similar behaviors, and in this case, changes in the behavior with neuromodulation. So first, we did a principal component analysis, and these are the top three shown here in this 3D plot here. And what I'm showing is the activity patterns in the whole network as a function of time in two conditions, one without neuromodulators as shown here at different time points during the stimulus onsets and the response onset, as you can see here in gray, and darkening as you go toward the final behavior shown here. And the same activity pattern, different activity pattern when the neuromodulator is present. And you can see it ends up in a different part of the space. Not too surprising because the behavior is different. But what is really the point I'm making here is that the tube of activity is non-interacting, non-intersecting. They occupy different parts of the subspace of activity patterns, which is really, I think, the key to what's going on. And in fact, if we vary the strength of the neuromodulation, and this is again for the fly simulation, you can see that those tubes move and remain non-intersecting over the range of neuromodulation. We further analyzed the network, and we asked the question of whether EI balance might be important, and indeed it was. So here what we're plotting is the threshold for, as you saw for the fly, what concentration of sugar water would the fly or the network activate the behavior, and it varied according to the network that we trained it on. And as you can see here, each of these dots is a different network. And each of the dots also is characterized by the total amount of the excitatory weights in the network divided by the total inhibitory weights, the rough EI balance. And what I'm showing you here is not the EI balance for the entire network, which in fact was flat, but only for the weights, the excitatory inhibitory ratio in area 3. Area 3 is the non-neuromodulated subpopulation of recurrent weights. Here's the neuromodulated. They didn't have any, there wasn't any correlation, or for the weights to or from those, but within the non-neuromodulated population, it was highly significant. And so there is an EI balance here that's working across the networks. Okay, so I want to first of all introduce the researchers here. Okay, I showed you at the beginning the archive paper that came out. Ben Suda, who's a graduate student in my lab, was really the lead on that, and Stefan Pate, who's an intern, helped out. And I also, the whole project got started actually at a meeting, which was held here, which was brought together people from modern AI, from machine learning and deep learning, and neuroscientists. And we had a symposium, and Hava Siegelman was one of the organizers, and Kei Tai, who's a colleague here at the Salk Institute, studies social cognition, asked the following question, after a lot of the talks, and said, well, what about neuromodulation? That's really important. And we know it's important in our brain. And the people in AI were flabbergasted because, of course, it never occurred to them that that might be something that would be useful. And indeed, that led to this collaboration. Hava at the time was head of a DARPA program in lifelong learning, and she picked up on it immediately. And so we all got together and came up with this project. And I think what it shows is something really important, which is that there's an enormous amount of flexibility in the way that brains organize behavior. And neuromodulation has been shown over and over again in the somatic gastric ganglion. Every important behavior is modulated, and it gives the brain a much more flexibility ability to shift gears very rapidly depending on the conditions. And this is also tied in with the emotional system. You know, how is it that emotion regulates behavior, and what triggers different emotions? And these are parts of the regulatory system in the brain, which is in this case global regulation, and that's going to become more and more important as networks in AI get bigger and bigger, and more of them. You know, we have probably 1,000 expert networks in our cortex, you know, just in terms of the number of neurons and synapses. And how do you regulate? How do you organize? You know, which of those networks is controlling behavior, and under what circumstances? And this is a different level. It's a systems level, and it's a level that we need to really think about. And we're coming to that point. If you want to be able to understand autonomous behavior, you know, the networks we have right now are not autonomous. They're basically coddled. They are fed data, and they are trained on very specific tasks. And this is not how brains are organized that to survive in an autonomously in uncertain environments. Now, of course, there are other parts of the brain. We focus here on the cortex. There's the basal ganglia. That's important for reinforcement learning. And that's the other problem is how do you organize 200 different brain areas so that they all coordinated? In any case, want to thank you for your attention and be happy to answer any questions.
No one else wants to jump in. I'll ask a question. I'm just curious, is there, I'm curious what the trade-off is between, you know, why is the brain doing this with the switching of behaviors with neuromodulation and not just with, well, it's just another input to this population? Because you could also train up the network that way, I assume, to just, all right, now I've got two inputs. One is the pulse and one is which task to do. What's the trade-off there?
Yeah, no, good question. And in fact, there are, I should mention that, in fact, there are attempts, and it's a perfectly good approach to use separate inputs to provide context. And that works too. But I think the problem, you know, not the problem, but what you're giving up with the trade-off is that you have to basically start training up a whole separate, you know, for different contexts. Like, you know, you'd have to have, if you have 100 contexts, you have to have 100 different inputs coming in. Whereas with neuromodulators, you can do it combinatorically. You know, you have 24 neuromodulators in different combinations, and you're constantly, and you're doing that very rapidly and extremely flexibly. And I think flexibility is something that is really of paramount importance. So, you know, you're dealing with the world. You can't, you know, so you encounter something new, and you have to come up very rapidly with a response. You can't just sit there and start learning with new data. You know, you have to really do that very rapidly.
So, Terry, I have a quick question, follow up to what you said. Rapidly, what is the time scale? And second, do we have specialized neurons that actually transport these neuromodulators in the different areas?
Yeah. Oh, yeah. No, they're separate. Each of these neuromodulators, well, first of all, the classical ones, there are actual nuclei that provide, like the nucleus basalis for acetylcholine, and you know, the ventral tegmental area, substantia nigra pars compacta for dopamine. You know, they come from different nuclei. In terms of time course, it had been traditionally thought that these neuromodulators are slow, and they are, because they go through second messenger systems. That is to say, they don't regulate the ion channel directly, which is what you find with regular neurotransmitters, but they go through intermediate intracellular messengers, which could be calcium or G-coupled proteins. And as a consequence, they are slower. But now what we've come to recognize, you know, through the kinds of experiments that Eve does, is that even these pathways, intracellular pathways, can be quite rapid, you know, in the second or sub-second range. Okay. So yeah, the neuromodulation actually, you know, it varies. And if if it's hormonal, then obviously that would be much slower because it takes a long time for for the neuromodulator to actually reach a lot of the neurons. But if it's targeted, it can be done very rapidly.
Could you show show the slide of the architecture of the model again?
Okay, sure. I will go back.
It's the one where you showed the two globs of RNN neurons. I guess that's a vanilla RNN or something.
Yeah. Okay. Yeah. Okay. I skipped over all the technical things because of the fact that I didn't have enough time to talk about all the things that I wanted
There you go.
to talk
Exactly.
about. And yeah, so this is a network with 200 neurons, and we start with random weights. We train it with we have 2 inputs coming in and we have 2 outputs coming out, and we train it with back propagation through time.
To what? To mimic this
yeah, so to mimic these 2 conditions, either with or without neuromodulation. And with neuromodulation, you can see here, this is the weights, the distribution of weight strengths, and you can see that this is without neuromodulation. And this is with neuromodulation. You can see everything shrinks by a factor of 2. And then we train the same input to give 2 different, completely opposite behaviors. You can see that the stimulus itself in the non-neuromodulated condition produces a go, output, but in the neuromodulated condition, it produces the no-go output, right? So it's a very different 2 opposite behaviors.
But the neuromodulation is simply a scalar input to the whole system.
A multiplicative input where we change the strengths of all of every single synapse in the network at the same time. By the way, Michael Hasler did some beautiful experiments in the 80s, and they should be better known. It's known that in the hippocampus, the neuromodulators have a huge impact on the state of the hippocampus, especially during sleep. And acetylcholine, it turns out, modulates the CA3 region, which is the highly recurrent part of the hippocampus. And it does it by strengthening the recurrent synapses and weakening the input synapses, from other parts of the hippocampus and the entorhinal cortex. And what this does is it causes the CA3 region to go into what are called sharp waves. And this is how activates a generative a replay of activity that then projects into the cortex. So here we go, changing the strengths of the synapses changes the behavior of the network, in this case, between receiving input, and being able to keep track of experiences during the day, and at night being able to play back.
But you don't learn that multiplicative factor, right? It's just literally a multiplicative factor that goes into all the synaptic strengths that's hard-coded. Exactly. And same for the stimulus?
Exactly. The neuromodulation was completely under our control. We did not learn the settings, and we assume that there are other parts of the brain that do that, right? Just like, we know that the other parts of the brain in the brainstem that regulate sleep-wake cycles regulate the neuromodulators projecting into the cortex that either activate it or puts it into a sleep state.
Thank you.
Eve, please. Yeah.
So I just want to add to what Terry said a little bit, because to my mind, one of the most fascinating questions that we don't really understand is what fraction of a network really has to be altered to get the whole network's behavior to change. So in some cases, you might have a modulator that might act on a relatively few number of neurons, but those effects can percolate throughout the whole network, and that will depend on the state of the network. Other times you might modulate those same number of neurons or the same number of synapses, and the effect remains local. And I think that that's one of the deep mysteries, to what extent local neuromodulatory action actually can influence a much larger global set of changes, and when it remains local to that particular pathway. And obviously you can think about it depending on the details of all the local circuits. You might have a way that it can really percolate out, and other times it remains local. And I think that's one of the big challenges for the future, to really understand how that works and under which conditions it works.
Yeah, I completely agree, and that's certainly the case in the mammalian brain as well. But I think Eve has a much better chance of actually answering that question in her preparation.
Well, you know, we published a little model that only has 5 cells, so you guys could implement it. And it's one of Gabriel Gooder's papers. And we actually did that exact experiment in the model. We modulated what we call a hub neuron and watched under certain network properties, it percolated and some it remained local. And, you know, that's actually, that study could easily be implemented since it was only a 5 neuron model with simple oscillators. And it gives you a real insight into all these problems of state dependent actions. So I don't know if you ever saw that paper. It was a Gooder and Martyr in eNeuro in like 2013 or 2014.
Yeah, it's often a lot easier to analyze a smaller network. And by the way, this is becoming increasingly important if you want to extract principles from the training. I mean, you can train deep learning networks to do a lot of different things, but you know, you're trying to dissect out, you know, how the performance arose is very difficult. But now we have tools and techniques for doing that, and more people now are able to dive in and work it out. And the idea though is that when you start modulating not just the strengths of the weights, but also the intrinsic properties of the neurons, and this is something that Rodolphe has really showed us, is that that gives you even more powerful ways of regulating. For example, acetylcholine regulates a neuromodulatory system which changes the gain of the neuron. In other words, for the given input, the amount of spikes coming out, and that's that's important for attention, for example. And that's very local, by the way, just the neurons that are being activated by what you're paying attention to.
So could I just ask to brainstorm a little bit, like if you wanted to use this for an artificial purpose, you know, I don't know, controlling something, you know, controlling a chip with oscillating neurons. And you wanted to use this kind of modulatory input, which could presumably globally change the synaptic strength easily just through the control of the bias current. Now, what form of experiment? Are you guys doing that kind of experiment in the group, Garrett? Could you comment on that?
Yes,
in
we have
what way you
projects
want to demonstrate this principle and its utility in particular?
Yes, so we have several projects here that and all those are in small networks, as Terry and Eve are getting out here, right?
But it's utility for purpose, right? In an engineered system.
Yeah, and so Rodolphe can say more about the overall the principles of neuromodulation control that we're embracing here. But Rodolphe, yeah.
Am I able to share my sharing screen?
Yeah.
So that's a figure of a paper we published in Biological Cybernetics. It's directly inspired from what the circuit that Eve was describing. So you have two HCO, one produces a fast rhythm, the other one produces a slow rhythm, and then you have the central hub. And so what is shown here is that you keep the connectivity of the network unchanged, but you can very easily switch having only one rhythm on and the other one off, or the opposite, or a combination of the two rhythms, just by modulating these intrinsic conductance in one of the HCO or in two of the HCO. So that's just one instance of the possibilities. How can you combine and how can you make two rhythms that, as Terry said, have an order of magnitude difference? You know, when you try to do that without this neuromodulation principle, it's very difficult. Try to design a dynamical system that can very smoothly transition from one rhythm to the other, or sometimes display a mixture of the two rhythms. It's very difficult. I don't know how to do that. And here it's just so robust and so easy. And so I think that's the type of thing that we would like to demonstrate in hardware. Yeah.
Okay. Yeah.
And now I think you can imagine that, you know, I mean, mixing two rhythms is sort of a very, very basic step towards engineering complex systems.
I would argue that it's quite easy to make clocks with digital logic, right? That's one thing that logic is very good at, is precise timing.
And I think that that's exactly where we haven't really demonstrated the functional use in AI, is because so far we are using clocks. So we don't need to emulate those analog clocks. But at some point, you know, if we really want to think of an event-based technology where we get rid of the clock, and the sort of, instead of using one central clock that dictates all the events, we have a mixture of rhythms. That's what we see in nervous systems, right?
Yeah, let me jump in.
You can think of each of these rhythms as a clock with its own scale, and that.
I'm sure you're familiar with GALS, right? Globally asynchronous, locally synchronous.
Yeah, sure. Yeah.
Yeah.
Yeah. So just to jump in on the idea of rhythms in our brains, it's chock-a-block. I mean, we have rhythms, you know, at many different spatial and temporal scales. Up until recently, these were, again, considered to be local oscillators. And in fact, you know, we can create neural circuits that do that. It's not difficult with little negative feedback. But what we now have come to appreciate is that it's also spatially coherent. That is to say, they're traveling waves. Every single oscillation, like I mentioned the hippocampus, there's something called a theta rhythm, 4 to 8 hertz. It's actually a traveling wave that goes down the longitudinal axis, like, you know, like clockwork. I mean, that's probably the most dramatic oscillation in the whole brain. But then, you know, if you go into the local circuits, you find higher frequencies, the gamma 30 to 80 hertz. Yeah. And during sleep, then it's all rhythms. It's basically that, you know, rhythm in the blues, you know, this is it.
So that makes me wonder, since silicon is, you know, 10 million times faster than biology, since the electrons are 10 million, how come you guys aren't working up at the regime of gigahertz or tens of gigahertz or hundreds of gigahertz, where this stuff is going to matter in silicon? Because, you know, the slow clocks are not.
Why biology isn't working? I mean,
no, I'm saying that in electronics, you have to think at the limits of performance, the electronics is going to be 10 million times faster. The ionic mobility is just 10 million times higher. And so you better be, if this stuff is going to be effective in future electronic systems, which are operating at the limit of the frequency of silicon, where this matters, because at low frequencies it costs nothing to broadcast a little clock. You know, that's the place where this stuff would seem like it would matter. You have processors really locally running at 10 gigahertz, and they have to communicate with other processors running at 10 gigahertz and twitching on and off rapidly. That's the place where this kind of stuff is really going to matter. It's coordinating those kind of subsystems at the limits of the electronics. That's where people are going to want to run it, right? Because silicon is expensive.
Wait, Toby. So didn't Carver, I mean, when he started the field of neuromorphic engineering,
it doesn't matter what Carver said. You always have to go back to what Carver said.
No, yes, you can hit the gas pedal.
He didn't know everything, right?
You get as fast as you can, but from an efficiency point of view, it actually makes sense to go slower because things get more efficient, right? So gigahertz is great, but in fact, there's been a trend towards lower frequencies.
What matters is performance, right? Number one is cost. Number 2 is performance, and number 3 is efficiency. There's 3 things that matter the most.
What performance you're talking about? I think it really depends what performance you're talking about and what the final thing you're trying to control has to do and what it's. So for example, in biological systems, at the final output, you've got muscles and you've got movements and things like that. And they're controlled at a frequency that's much, much slower. So, and the other really important thing, and I don't know how this is relevant, it's been known for years and years and years and years that oscillators like the one that controls your heart is usually healthier when it's not perfectly regular. So there was an old stuff about chaotic regimes in cardiac physiology being more healthy than perfectly regular ones. And one of the first signs of disease is when you get too regular. And there's something about that which sort of argues that building a perfectly regular digital clock is the last thing you might want to do in some kinds of applications.
In physiology.
But there may also be applications that I don't know enough about where there's some benefit to having some.
Well, no, you're right, Eve. If you want to run at the limit of the power supply where you turn the supply voltage way, way down, then the clocks are going to start to jitter more. There's going to be more timing jitter and stuff. And, you know, then things should be robust to that jitter. Yeah, I just think.
So there are all sorts of really issues. But I think if you think about running at the low power level, which may end up being very important for certain kinds of devices. You know, if you're thinking about a device to live inside a human being for 10 years, you really don't want it to use a lot of battery power, right?
I mean, Eve, they run a pacemaker for a decade on one battery and they're clocking it, you know, at 30 kilohertz or something. It's not a problem. It's really not the dominant energy consumption. You know, running these low frequency clocks across a piece of silicon is not, because the electrons are so fast, it's not that it's overrated as a power consuming thing in electronics. I just think that you should be thinking at this regime of things working at their limit of frequency, where local variations.
By the way, biology can run things at a higher rate. For example, if you look at electric fish, they can produce kilohertz, you know, continuous frequency output, right? And with extreme precision, 1 part in 10 to the 4th. So yeah, you know, biology, when it needs to, can create very precise oscillators for the needs that it has, if needs be. But and you know, but I go along with Eve, which is that look, if you're dealing with the world which has slow time constants, right? There's nothing happening in the world that's at gigahertz that you have to respond to. So you're better off having machinery that runs at that level and is using time itself. You know, time is its own representation, going back to Carver Mead.
See, there's one problem with that, Terry, when you're talking about silicon, is silicon costs money, real money. And since silicon is so fast, it makes sense to time multiplex it. And so therefore, you know, just use that's the lesson.
Okay. Well, no, that's completely separate. Okay, that's completely separate. And
yeah, but that's a fundamental limitation, right?
Oh, no. If you want to, then yeah, you could run 100, you know, by multiplexing, you could run 100 different circuits, you know, sequentially, and that's how GPUs work, right?
No, computers in general, right?
Yeah, but you know, that's taking. You're right. That's taking advantage of the time constants you've got there, but you know, the price is robustness, right? You've got to deal with circuits that have to have incredible precision and you know, designed to have very.
It's true.
I mean, temperature and so forth. No, I mean, you know, it all depends on your goal. What is it you're trying to optimize?
But I guess, Terry, Toby, the way I understand your question is you are suggesting that because silicon works at such a high frequency, perhaps neuromodulation is irrelevant for. Not
irrelevant. I think it's relevant at those high frequencies.
But to me, it's
not at low frequencies where it's so trivial to clock things. And established, and all the tooling is there, and everybody can produce things easily with clocks running at low frequencies. Just push it up to the cores, you know, where I don't know. I mean, that's what I would work on, at least, because then you'd be up there with the state-of-the-art technologies, you know, 3 nanometer, and then you could raise money for it too. That way, you could easily raise money for it by selling that story, right?
To me, the absolute scale at which you work, and whether it's different in technology and in biology, that's not too much of an issue. I think what is amazing in biology is the span of scales and of interacting scales that interact very reliably over several orders of magnitude.
Yeah.
That's very hard to do in technology.
Yeah.
I think neuromodulation is really exceptionally robust and reliable in that regard.
Oh.
And in fact, it's funny that in our interaction with Gert, the toughest things at the moment is to slow down the time scales and to get this span of times of interacting time scales, to have in the same chip things operating at the milliseconds and then at 10 times slower. That's hard.
Yeah, that's hard. I agree.
And in biology, this is where you see this. You go from neuromodulators and then hormones and then and you can continue and you get time scale that span 2 or 3
okay,
or 4.
so Toby, let me give an example that I think is directly relevant to what you work on, which is that we have a visual system that can deal with light intensity over like 10 orders of magnitude, right? I mean, to the darkest skies, to the brightest sunlight, and it's actually done through a lot of different circuits that are adapting, both in the photoreceptor as well as the circuits in the retina and back, your pupils and so forth. And so biology is really putting together a wide range of systems at different different layers of processing at different timescales. And that's, I agree with Rodolphe completely that's a non-trivial problem that has to be solved. You're as you know, if you put a camera into a dark room and then try to shoot through a window, you get black in the room, or if you do it on the room, you get white in the window, right? I mean, that's because cameras just can't adapt over that range.
Not sure exactly what the relation is with neuromodulation here, but yeah, I can see how you want to modulate the time constants of the parts of the retina, for instance, to adapt to the light intensity, for sure. Yeah, the neural circuits need to be modulated. I mean, that's how I would be interested, right? As an actual user with cameras like this, this one here, playing with it almost every few days, trying to play around with algorithms to make it work better. I like the modulation, right? I like to do gain control on it and stuff, but that's different than controlling oscillators and getting them to self-oscillate and stuff like that. I mean, it's related, but it's not.
That's a surrogate.
It's simpler, much simpler.
That's a surrogate for dynamics. In other words, oscillations are very important. Central pattern generators in general, very important for many different circuits in the brain. But you also have to control much more complex behaviors, reaching, being able.
I'm just telling you, I just think that Gert could easily write something up and sell this stuff, pitch this stuff, running at 20 gigahertz in TSMC, and then raise a bunch of money from SMC.
I agree with that. And my guess is that, if you just scale everything up in terms of speeds, you can, now you can neuromodulate at microseconds, right? So,
no, picoseconds.
Okay. No.
And they can run
so that would be,
data, right?
That might be fine for doing some kinds of circuit switching, you just take 5 billion times faster, the principles we're talking about. But in biology, there's another piece of this, which is a lot of the same cellular mechanisms that are engaged in neuromodulation and that are further engaged in long-term control of excitability, et cetera, are also parts of the molecular pathways that allow nervous systems, cells to repair themselves and replace themselves. So remember, the brain is constantly rebuilding itself, and it has to rebuild itself with processes that take place over days and weeks and years. And so the process, in order to get those processes to be properly engaged by activity, you basically, the back end of the segue in timescales is the long-term regulation of neuronal activity through cells rebuilding themselves, replacing ion channels and stuff like that. So biology has timescales that go from milliseconds or sub-milliseconds all the way up to, we'll call it months and years. And all of the same cellular mechanisms are engaged in different ways throughout those timescales. And I think that's a fundamental, and you have to do that if you want an organism to live for 100 years, because proteins don't last for, a big turnover in weeks and months. So that's a constraint that, in a sense, is built in long-lived animals, that there's no particular reason for electronics to have to deal with until such time as you're asking their chips to rebuild themselves.
No. Actually, it already occurs with chips. I mean, mismatch, right? So one of a concrete example of what Eve is talking about is homeostatic plasticity, right? So this is a form of changing the strengths of synapses in order to keep neurons within some balance so that they're not up against the rail, right? Or way below it. And it's very slow. It takes hours, days for these changes to occur, but it maintains stability over long periods of time. And Eve is absolutely right. It includes not just state stability in terms of the circuit, but also regeneration. When things go wrong, you have to have new synapses created, and you have to have new circuits reorganized. So that may be even more difficult, more important.
So Garrett could sell this. Garrett could sell this as a way of dealing with electromigration in advanced processor cores. When the electrons bump along the metal, they move the metal atoms along, and eventually at high current levels, the wires break apart. It's actually true. It's not a problem because people aren't working at those high current levels, but that's the aging mechanism in silicon chips. I don't know if it's still a problem, but it's definitely a problem that if you make the wires too thin and you run big currents all the time in one direction, eventually you get these cracks in the wire just because the atoms get knocked out of place.
If you run a big current and then a small current, does the crack relax back to?
I don't know if it's possible to anneal it out. I really don't know anything more than what I just said because I've never experienced it, right? We don't run our chips at those, but it's a problem for big processors that consume a lot of power. Right, Garrett? You know much better than me.
It would be hard to sell this to, there are other ways of doing all that, right? But so
you can pitch it.
So we can try to push things in the gigahertz regime, but with scale, this neuromodulation is really playing out to bridging scales, as Terry was mentioning, right?
Yeah, you're right.
As a mechanism that can act over very large spatial scales. The example of the dopamine system is a very good example, right? There's you can have very locally acting neuromodulation, but this global action is quite important, and that's a mechanism that can really be embraced here.
Thank you.
Can the audience make a comment?
Yes,
from the very practical viewpoint of engineering, if you want to do, for instance, brain-machine interfaces, you don't need to do gigahertz, right? You're going to be interacting with the timescales of the brain. And it's still important to understand neuromodulation at those timescales because you wouldn't need to speed things too much to effectively, let's say, control some parts of the brain or something. So, yeah, also there's some value in speeding things up, right? There might be some value in that, but at the timescales of the brain, I think that it's already very important to try and understand it from an engineering point of view.
So I have a question, which is, given that neuromodulators are constantly shifting, do you see that when you are, BCI? Do you see that there are shifts in the your transfer function from the activity to the behavior? Is that change with the person's state of arousal or thirst and so forth?
There's a whole different field here. If you Google search neuromodulation control, it brings you to basically all those deep brain stimulation or those Medtronics type of devices, right? And there's a clinical aspect of all this, and John Doyle was talking more about this on the discussions on Slack here. But yeah, neuromodulation is used as a means for neurofeedback or for regulating the nervous system clinically too, and that's an entire different aspect here. Right? We haven't touched on this in this workshop, but clearly neuromodulation has huge effects on brain states. Right?
Except that even like the methods that they use for DBS, for deep brain stimulations, they're very basic, exactly because, you know, neuromodulation is, you know, we still need a lot more understanding to be able to use this knowledge in those clinical situations, right? Yeah.
One thing that this suggests to me, and probably others have already thought about this, is that many of these circuits are operating at the edge of chaos in such a way that the neuromodulator can kick them into one oscillation or another, or one set of inputs to the network can kick it into one set of oscillations or another. I think Walter Freeman was one of the people who promoted this idea for brain EEG and oscillations, but maybe it's something that we need to be thinking about as neuromorphic engineers.
I myself would not build a device near the edge of chaos. I think that is a dangerous place to live. I think that concept is a little bit oversold, although it is true that you need to have fluctuations. You have to be working in a regime where, you know, there's background activity and there's a lot of flexibility near threshold. But you know, if you're talking about the formal definition of chaos, which is deterministic chaos, then I think that's a different regime.
Yeah, I was thinking in terms of, like Eve mentioned the heart, for example, being operating.
At least irregular. At least being irregular.
Yeah. No, go ahead, Eve.
I think one of the interesting questions that we always puzzle about is if you build models of oscillators and you ask, and Mark Goldman many years ago worried about this a lot, is where would you want to be living if you want to be both optimally stable or stable enough and close enough to changing state so that a modulator can take you across those boundaries. So you probably don't want to be right on the boundary where you can run into too much bistability that you don't want. But if you're too far from the borders, then maybe, you know, it takes too much modulation or too much effort to make the state changes that you want to make. And so I think there's a really set of interesting questions about where, if you're going to be modulated, how far from the bifurcations that you think are constructive ones do you want to be sitting? And, you know, obviously you're not going to be exactly the right, you know, you're wandering around in those areas, but I think it's a really interesting question that we don't really understand very well. Maybe Rudolph does, but I don't. How far you want to be to both be sensitive enough to modulatory control, but also to be relatively safe, because you don't want to randomly go into too much bistability.
Well, that's completely true, and I think that's why we should not think of central pattern generators as oscillators, but instead we should think of them as excitable systems. It's always about the threshold properties that matter in the end. And there are different ways to build oscillators. There are oscillators that don't have thresholds, but I think that's the neuronal oscillators are very specific in that. In fact, it's their excitability. It's already true at the single spike level. Sometimes we think of a neuron as that is either silent or oscillating, but the real function of a neuron is just to spike. It's excitability, and the oscillation is sort of just one end.
So another data point with regard to the heart is that the fluctuations there are on a beat by beat time scale. That is to say, the intervals between beats is variable. right? That's what's important, the fluctuation in the intervals. And
Absolutely.
that's not what you see with deterministic chaos.
Right, and of course they're averaged out anyway. By the time you start looking at cardiac output and what's going on in the periphery, probably that cycle by cycle, variability is sort of largely
it is averaged out, but I think it's giving us a hint as to the control system.
Yes, absolutely. But if I look at the amount of oxygen in the capillary,
that's not changing.
That's not going to be changed. But on the other hand, there may be some advantage to the way blood. I don't know enough about blood flow and stuff like that to know whether there's actually an advantage to having that little cycle by cycle.
Actually, there is. So it's just a technical thing about heart rate variability. In fact, your heart rate accelerates just a bit when you inhale. And there's a name for this. And the rationale for that in principle is that you want to have a little more blood flow when you're inhaling to get more oxygen transfer. But there's a countervailing thing, which is you also are using your heart rate to adjust blood pressure. So what happens is when you inhale and exhale, you actually drive blood pressure changes in your thorax. And so the heart is controlling that. And it's really extreme in athletes who have really low heart rates. So people who have heart rates in the 30s have this extreme heart rate variability. And what's interesting is those two things are both happening at the same time. And so you can vary them by changing how you breathe. And so, but what it reflects, so again, this is just the math. This is nowhere near the edge of chaos. It's as far from the edge of chaos as you can sort of imagine if you just pose it mathematically, because it's very, very responsive to this homeostatic regulation of blood pressure and oxygenation. This is a rather kind of poorly understood subject, unfortunately. But in engineering, for sure, there's almost nothing near the edge of chaos except in, say, cryptography. And that's just a math question. I think there's something about it philosophically that has some appeal, but technically what that word means and what it has meant, nowhere in engineering, and I doubt that it's anywhere in biology.
Maybe chaos is the wrong word, but by having this variability, does it make the system more adaptive to changes that are needed on the spot?
So if you say leveraging variability, that is kind of intrinsic to these systems, and you can't get away from it. You've got to do the control system so that you leverage what variability you have and suppress what you don't want. And the problem is the mechanisms to do that, just mathematically, are nowhere near chaotic. I mean, it's just, so variability and chaos are extremely different things.
Okay.
But all of this could be made much more precise, and it's been neglected, I think. But I think Rodolphe's take on this in the context of spiking neurons is, again, I totally understand it. I'm trusting him because I know he's going to get this right. But that's a really great way at looking at what we would think of maybe otherwise as near chaos, this excitability, this ability to be near thresholds. It's about managing variability and thresholds. So it's at the edge of something. It's just not chaos. And I think we need to be clear about that, because it's easy to understand what the edge of chaos is and mathematically investigate whether something is or isn't. What Rodolphe is getting into mathematically with his models of spiking neurons is much more subtle and much more biologically plausible and much more interesting. But the math is much deeper and harder.
I think a central difference is, without entering into the details, is that we need an input-output concept. And instead, the concept of chaos is a concept for closed systems, for isolated dynamical systems. And that's why
another good
the
point.
concept is very poor and very hard to apply to biological systems, because we can never think of a biological system as an isolated system. But the concept, the mathematical concept of deterministic chaos only has a meaning for an isolated system. It's not an input-output concept. I think that that's a fundamental distinction.
Yeah, so for example, if you disconnect the heart rate from blood pressure and all these other things, you can smooth it out. It doesn't vary anymore. It's varying because it's doing control. It's a little bit like, you know, the brakes and engine in your car. When you're driving around, it's fluctuating like crazy. But that's a reflection of the job it's doing in keeping you from crashing your car and getting where you want to go. And it just doesn't have anything to do with chaos.
That note, I'm going to let the conversation, because we are we're getting into the time where other meetings are scheduled, so I do want to bring this to a close. Please continue the conversation in the Slack channels.
Very good. And the neuromodulation control group will move over to a recurring Zoom link, so we can continue some discussions and project discussions over there. Thanks, everyone.
Great. Thank you all.
Bye, guys.
All right, bye-bye.